Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on September 17, 2025, about 3 days ago. The standout idea is a behavior foundation model that unifies whole-body control by treating every task as generating behaviors toward a goal, so a single generative model can handle motion tracking, teleoperation, locomotion, and more without task-specific reward engineering. The paper is titled Behavior Foundation Model for Humanoid Robots, and as we will see later, the results are really promising. The model learns from large behavioral datasets, supports flexible control masks and a latent space for composing motions, and adapts quickly to new skills via residual learning. On X, posts highlight the behavior foundation model unifying whole body control and reducing reward engineering via a generative conditional variational autoencoder, with quick adaptation to real scenarios. One announcement video and demo montage draw moderate engagement, roughly 140 likes. The previous segment highlighted social buzz around the approach. Figure 1 shows a montage of real robot behaviors that the model executes zero-shot, which means the robot performs skills without task-specific retraining. The top row presents everyday motions, like a swimming pose and sitting down, while the middle row covers standing up and a butterfly kick, which stresses balance and air time. The bottom row illustrates new skill acquisition, with a forward roll and a side salto, so the range spans gentle poses to acrobatic moves. The previous figure showcased outcomes. Figure 2 explains the pipeline that makes those behaviors possible. Panel A depicts human motion retargeting that maps motion phases into a humanoid. Panel B outlines proxy agent training through motion imitation, so the simulator learns rich skills with privileged inputs. Panel C introduces the unified control interface and the mask strategy, which toggles root, key points, and joint angles to represent different control modes. Panel D presents pre-training with a conditional variational autoencoder, where online distillation and a latent prior guide the decoder to output actions from real proprioception. The previous figure laid out the training pipeline, and Table Y now specifies how the proxy agent was shaped through rewards and penalties. The task reward emphasizes accurate body and feet positions, body rotation, and velocities, while penalties down weight torque and joint velocity limits and attach a large cost to termination, which stabilizes learning. The regularization block moderates torque, action rate, and foot behavior so motions stay natural. Table 2 then lists domain randomization ranges and push disturbances, which make the learned behaviors transfer better to the real robot. Alright, the previous figure detailed training choices, and Table IV now reports locomotion accuracy across 3 datasets. The table presents linear velocity and yaw angle errors, which measure how well the robot tracks target motion. Specialist models win on a mass train, but they drop on a mass test, so they overfit. BFM achieves the best or second best scores on a mass test and 100 style, with notably lower yaw error than HOVER and reinforcement learning from scratch. The consistency across datasets signals stronger generalization. Alright, the previous table covered locomotion, and Table II compares virtual reality teleoperation and motion tracking across 3 datasets. The table reports joint and key point errors, plus linear and angular deviations, so lower numbers mean better tracking. BFM delivers the best or second best scores on a mass test and 100 style, while specialist and HOVER models slip. The behavior modulation block shows guidance coefficient lambda around 1.0 to 1.5 further reduces motion tracking errors. So, the previous table compared teleoperation and tracking metrics, and Figure 3 illustrates why the approach scales beyond single tasks. Panel A demonstrates behavior composition by linearly mixing 2 latent codes, so a walk gains a turn or a kick. Panel B maps a structured latent space where clusters correspond to walking forward, backward, and side steps, which enables smooth interpolation. Panel C shows behavior modulation that stabilizes a tricky landing. Panel D outlines residual learning on top of the pre-trained model, and Panel E reports faster convergence and lower key point error than pure reinforcement learning. Alright, 2 takeaways stand out. Behavior as a shared objective lets one generative model span motion tracking, teleoperation, and locomotion, and the conditional variational autoencoder with mask control enables quick adaptation and even latent space composition. The broader implication is simpler, more general humanoid control that can learn new skills fast. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.